Nanopillar lasers for the realization of optical interconnects. And so basically just the flow of how I'm going to present the material. I'll present my abstract, the motivation. Then I'll just briefly go into the advantages, requirements and challenges facing optical interconnects, and then present the idea of the nanopillar laser as the on-chip light source, and then wrap it up. So in reading the feedback from my abstract, I realized that maybe the idea was clear to me, but I didn't convey it precisely enough. So what I'll be focusing on is the integration of an on-chip light source to realize optical interconnects as a replacement for the current copper interconnects. So we're all familiar with Moore's law, which basically says the number of components per chip doubles roughly every 24 months. And this means that as the components become more dense, the feature size decreases. And this is a good thing in terms of cost, but it has an adverse effect on interconnects, on-chip interconnects. And the purpose of interconnects is to distribute clock and other signals, as well as provide power and ground connections to the various functional blocks of the integrated circuit. And the International Technology Roadmap for Semiconductors report states that the fundamental development requirement for interconnects is to meet the high bandwidth, low power signaling needs without introducing performance bottlenecks as the scaling continues. But as the scaling continues and the feature size continues to shrink, copper interconnects are introducing performance bottlenecks. An example would be there's a speed bottleneck that results from a combination of gate delay and interconnect RC delay. And the RC delay becomes dominant and increases with the decreasing feature size. So that would be an adverse effect on the interconnect. So the report also proposes potential replacements to the copper interconnects, which would be nanowires, carbon nanotubes, graphene nanoribbons. There's a wireless scheme that involves antenna and signals, and then there's an optical scheme. And while all of these have several advantages over the copper interconnects, they're still very immature in the research, or they have they face some challenges that keep them from being completely implemented. So I was interested in the optical interconnects. And basically, with the optical interconnects, data is transferred as light, or like photons. And some advantages of this would be that speed of light signal propagation, larger bandwidth, low power and latency, and noise immunity. So some requirements for the optical interconnects. The system as a whole that would complete like the data path is called an optical link, and it consists of a light source, couplers, modulators, waveguide, and detectors. And the light source generates photons with a specific wavelength and sends it to the modulator, which is like a transmitter, and converts that signal to optical signals in terms of the intensity. And from there, the light goes to a waveguide that acts as literally like a guide to guide the wave, or if the wave is not straight and it needs to go a different route, it acts as like via mode of transmission. And then from there it goes to the detector, which is the receiver in the whole system, and converts that light into a photocurrent that can then go and be used how it needs to be. So major challenges facing optical internet. The major challenge that optical interconnects face is the coupling of light from an off-chip light source into the submicron chip waveguides. And this causes optical loss, and the precision required to align the off-chip light source with the waveguide, the on-chip waveguide, is difficult and can be expensive and impractical for mass production, which is the additional challenges of cost and complexity of the system. So one way to fix this is to have the on-chip light source, and so you get rid of needing to align the off-chip light source, and therefore reducing the complexity of the system. So there are three criteria for ideal on-chip light sources, and one is that it has to be silicon CMOS compatible material and compatible with the way that CMOS are already fabricated, and the light oscillation has to operate at room temperature, and the preferred emission wavelength of the light emission is in the near infrared, which is 800 to 2500 nanometers. So there was recent research that developed a way to grow a nanopillar laser directly on the silicon, but they haven't implemented that in this way. They just show that it can be done. So what it is it's just indium gallium arsenide hexagonal column that's kind of tapered, so it's not exactly a column. It's kind of like a cone, an upside down cone, and the height and diameter of the nanopillar can be easily scaled and controlled with the growth time. And since it's very small, it's optimal for high density usage on the silicon. So these nanopillars do in fact meet the three ideal criteria because they can grow at low temperatures. At a low temperature of 400 degrees Celsius by the metal organic chemical vapor deposition method, and so that makes them easily integratable with the silicon electronics without compromising the transistor technology that may already exist there on the CMOS device. And the laser oscillation operates at room temperature, and the light emitted is in the infrared range between 890 nanometers and 930 nanometers. And there is a way to control what wavelength you want by increasing or decreasing the amount of indium in the composition during growth. So more indium would give you a higher wavelength. So in that way, you can control what wavelength, and also by varying the growth time, you can control the size of the nanopillar. So using these on the oh, I guess I left one slide out, but I did. Okay, so I want to say here that the way that it was shown to be grown was using the MOCVD method, but that means that you can't selectively place the laser where you want it, and you really wouldn't want that, because if you have an optical link, you want to place the laser in one place and guarantee that it's going to be there. So I was thinking that you could use a selective area growth method where you would use a film and specify the location of the growth of the nanopillar. So once you would be able to specify that, these nanopillars emit light in the in-plane radial direction. So other technologies that have already been developed are compatible with this, such as like an in-plane waveguide. Because you can grow these at low temperatures, they can be integrated after the electronics fabrication. And like I said before, using the on-chip nanopillar laser eliminates the need for the coupling of the off-chip light source, thus reducing the cost and complexity. And that's it, yes. But I had another slide, but that's it.
Questions?
Yes.
So, would there be a delay after, I think what you're proposing is you will take the off-chip signal, you'll use this nanopillar laser to convert it directly to light and then continue on that way. Is that correct?
There is no off-chip light source. The growth of the nanopillar laser is the on-chip light source and eliminates the need for the off-chip.
What I'm saying is you would take a signal off-chip, say a signal from a different chip, and then turn it into light. Is there a delay involved in this?
Actually, I was only focusing on the on-chip for like intra-chip communication. So I think between chips, like from that's what you're saying, right? Like
yes.
From another chip. Well, I suppose that because if it's optical, there would be a very negligible delay, if any.
Can you explain again why we use nanopillar laser? Why we use that? Why we need that?
Oh, because it provides the on-chip light source as opposed to having the off-chip light source. And using the off-chip light source brings in it poses other problems, such as having to align the light on the chip to the waveguide by using couplers. And because it's so small, it would be high precision alignment, which is difficult to achieve.
So what is the application? Why we need a light source? Common CMOS, for example, IC fabrication. Why we need a light source?
Because it's what produces the photons. It's kind of like the information carrier. It takes the electrical data signal and then it goes into the receiver, the modulator that turns it into the signal to send optically through.
So you mean we have like a traditional CMOS IC, and the source is photon, not an electron. That's what you need.
Right, but it's all in one.
So the transistor and the existing device working on
yeah, they're all working
photon?
together. Yeah. No, like they're. Should have done a picture.
Can use blackboard.
Okay. Over here.
The base part.
Okay. So like you have the. And then it's the light source, and it sends here to a modulator. It takes the signal, and it takes the light source takes the signal and it modulates it through the waveguide. Like there would be a waveguide here to the photodetector. So it's like they work together. I don't think that I'm explaining it right, but like I know what you're asking, and I don't think that I'm making sense of it like clear enough.
So you're saying the electrical signal from the transistor gets converted into light by the nanopillar laser,
Yes.
and then that light gets detected by a photodetector, which will again convert it back to an electrical signal for another transistor to process.
Right.
Okay, so this is alright. So this is what happens inside one chip, right? So if you have to talk to another chip, it's still electrical between two chips.
Correct, but currently there are technologies that do connect between chips optically.
Okay.
Like they have already come up with those.
Okay. But this proposal is basically on chip one, right? So
Right.
It's only for interconnects on the chip.
Right.
So you eliminate the delay of the electrical passing through the copper interconnect one.
Yes.
That makes sense.
So I have one more question. So we need a wavelength of 890 nanometer to 930 nanometer. So why we need that wavelength? Just in your slides, you said we need that wavelength. So I don't understand why we need that.
It's just because most passive components operate in the infrared wavelength, and the nanopillars emit in the infrared wavelength, so that makes them nanowave.
Would that depend on the frequency of your IC? Like if it's a high frequency application, for example, would the same wavelength work, or would I need to change the wavelength of the light?
You know, I'm not sure.
Okay.
I think you would have to change the wavelength, but you can tune the lasers by varying the amount of indium in the growth process or the growth time. So they're tunable, and
So when you fabricate the laser, you mean do we use a silicon-based substrate or other?
yes, yes.
So we need to some dopant, right, to
I'm
make
sorry?
lasers. Silicon doesn't make very inefficient, so we need to dope some material, other material to make nanopillar laser, right?
Yeah, they're indium, gallium arsenide.
Any other questions? So, Kevin, you are just talking about the light source, and you are not really worried about how that light gets to the other decoder, so to speak, right?
Right.
Because your rationale was the interconnect relays, right? But you haven't talked about interconnects. You talked about just the light source.
It's they don't currently have these on-chip light sources. So, like this would, what's the word? Kind of push along the way, kind of help the whole realization of
Right.
the whole.
So only if we have channels for this light to move from one point to the other. Right? So you have
Like a waveguide?
waveguide, maybe, right? I don't know. Maybe it's just fiber optics, which is again a guide for light.
Right. Oh, yeah. The waveguide it can be like fiber optics or like in plane. They have graded ones, but I'm not sure what your question is.
So the question is, your rationale of the proposal was that interconnects have their problems, right?
Mm-hmm.
But you haven't talked about replacing interconnect. You're talking about light sources.
Right, but it helps. The light source was the main challenge. Is the main challenge in realizing the optical interconnects.
But they have done the rest of the thing?
I'm seeing like more forward. So once.
But you can't move forward without the rest of the thing. So either when you talk about interconnects, then you have to talk about, okay, you're going to create light, then you're going to transfer it somewhere. And one of them asks, okay, so you need other components also in there. So just an LED is not the answer. It's just one sub part, which is hard to make, of course, but it's not the solution of the total problem that you started with, which was the interconnect problems.
I see what you're saying.
Right?
Yeah,
Make sense?
Yeah.
So it has to be a little more than if you are trying to solve that problem. I can say, okay, there is a problem in getting from Nanopillars Hall to Wolf Hall in heavy rain. So unless I provide a way of getting from here to there, it doesn't matter. I can say, okay, go up and down 6th floor to 1st floor in Nanopillars Hall. You will never reach Wolf Hall. Make sense?
Yeah.
Have to have some way, okay, now you have to identify the problem. It's how to get there, but how do we get there? I can tell you, okay, go down to the 1st floor, that's the first step, but then what? Yes, we have to go to 1st floor to go outside the building, but then what? So don't you think there's missing some critical sides to it?
Yeah.
All right, let's thank our speaker and let's get to the next one. Please, next. Lynn, can we go next?
You need to connect them to the CPU.
Sure.
It won't show up otherwise. No, down.
Why don't you hook it up directly into the CPU?
Into the CPU.
Look right, look down.
Oh.
On your right, so there's a black box.
Okay. Which one to make it large?
You can push F5.
F5, okay. Okay. Thank you. Hi, my name is Charlie. The topic I'm going to present is replace RCA with total dry cleaning. RCA cleaning has improved over the years, but its disadvantages still remaining, such as cost, environmental impact, and recontamination during rinsing. And in the meantime, advances in technology push RCA to its limits, like tighter geometries, thinner films, and more stringent cleanness requirements. So the dry cleaning is the direction. It has lower cost, fewer environmental hazards, and tighter geometry penetration. Here is the RCA cleaning. What we did in class. Preliminary cleaning is to remove photoresist using sulfuric acid. SC1 is to remove organic contaminants using ammonium hydroxide. And after SC1, usually oxide is formed, so hydrogen fluoride is used to remove oxide after SC1. Then the last step is SC2. It's to remove ionic contaminants using hydrogen chloride, and every step followed by rinsing. And in the last step, and the wafer is blow dry. It's RCA modification, a lot of modifications. The chemicals concentrations have been reduced. The purity of hydrogen peroxide is increased, and so no metal, especially aluminum. And the other one, the other modification is the surfactants and ozonated DI water. Also, modification and improvement. The inherent RCA has inherent shortcomings. There's like particle generation, dry difficulty, high cost, chemical waste disposal, and recontamination caused by rinsing. And most importantly, it's unable to penetrate into deep and narrow trenches due to surface tension. And the technology, new devices also challenge RCA. The new devices require cleaning technologies must be able to remove particles smaller than 0.1 micron and reduce metal concentrations below 10 to the power of 8 atoms per centimeter. And each thin oxide is with only 1% variability across the wafer. Use a cleaning agent that can permeate into extremely tight geometries and maintain a surface with total roughness less than 5 angstrom. The advantages of dry cleaning: the chemicals are purer. Dry chemicals are more easily protected from contamination. Dry cleaning uses less chemicals. Dry cleaning penetrates tighter geometries, and dry cleaning process is easier to integrate with the subsequent processes. I use 3 dry cleaning techniques, actually 4, to replace each every step in RCA cleaning. Use UV ozone cleaning can replace both 2 steps in RCA, preliminary cleaning and SC1. The hydrogen fluoride can replace hydrogen fluoride water solution. And UV exposure of wafer in chlorine plus cryosol spray techniques can replace SC2 to remove particles. So I use 2 steps because dry cleaning doesn't remove particles very well. So I use 2 steps. Here is a system, UV ozone system. I call the process standard dry cleaning. SDC1 is a UV ozone dry cleans, preliminary clean. SDC2 anhydrous hydrogen fluoride clean, removal of organic films, metals, and particles. SDC3 remove particles by UV exposure of wafers in chlorine. SDC1 is UV ozone cleaning. Exposing wafers in an ozone environment to UV causes carbon to volatilize. Because photoresist basically is carbon, so it can remove photoresist. It's efficient in removing photoresist and other organic films. But in the meantime, it also rapidly oxidizes wafer. So after its process, a dry hydrogen fluoride must be used to remove oxide, just like RCA clean. Its process could be costly due to the power source. The power source is needed to create plasma. The second step is to use anhydrous hydrogen fluoride to remove oxidized formed in the first step. It also removes metallic contaminants and particles. The effect will be improved by adding anhydrous hydrogen chloride. The last step is to remove particles by exposing wafer in chlorine. Yes, 3 mechanisms is volatilization of metal chlorine, formation of volatile complexes, and left off. It's the first part of the third step. The first step, chlorine gas is introduced into a vacuum chamber at 5 torr, 40 degrees for 30 seconds. Under its condition, copper chloride CuCl2 is formed. Then, no vacuum. Then the chamber is then vacuumed, and to 45 nanometer of ultra UV light is introduced to reduce CL2 to CL. The later one can be volatile, so it can be removed. Then the temperature is raised to 135 degree to remove iron and FeCl2 and NiCl2. Those two are volatile. Can be volatile at 135 degree. Then at 170, the temperature is raised to 170 degree, and aluminum chloride can be removed. And finally, hydrogen fluoride and chlorine gas are reintroduced into the chamber to remove oxidized Fe and Ni. And the second step is to use cryosol spray techniques to remove any other particles remaining, including group 1 and group 2 metals. Its technique is to bump wafer surface with high velocity cryosols. Cryosols are formed by rapid cooling gas such as argon. The mechanism is kinetic energy is transferred from cryosols to particles, and cryosols absorb heat once subliming, and particles dislodge due to the difference in expansion coefficient between particles and the wafer. The novelty of the paper, when people talk about dry cleaning, they talk about specific application. But I didn't see anyone systemically replace every step in RCA using dry cleaning. The second one is I use two-step process to remove particles. When they talk about dry cleaning, they just say it won't work because it doesn't remove particles very well. But if you multiple steps, at least a two-step I used, it will help improve the effect. Okay. Okay.
So what is the limitation or disadvantage of this process?
Excuse me?
The limitation or disadvantage of this dry cleaning?
Like the professor said, it could be costly to use UV ozone to produce plasma. It costs power. It uses a lot of power. I think the other limitation may be the cryosol technique. Probably do not work very well to remove group 1 and group 2 metals because they are bonded with wafer with ionic bond, so, a little bit stronger. But they are small. The group 1, group 2, like calcium, sodium, potassium, they are small, so it still can be removed. So new mechanism needed to be. In my paper, I wrote something about future research.
How do you think about the throughput? I think it's not good for mass product. production. So,
Oh, it's for single wafer. I mean,
slow. I mean, process is slow.
yeah, basically it's for single wafer, but it can be, the system can be developed to process batch. I think, like.
Do you think that this dry cleaning has more advantage compensating disadvantage? Like,
Yes, absolutely.
It's
The industries how the industry has been working very hard to go that direction. Okay.
So what is in the cryosol spray you propose to use? Is it just argon, or is it argon plus something else dissolved in it?
I think it's some gases. When it's cooled, it can be reduced to liquid. That's it. But I don't know for sure. But argon absolutely works.
I see. So you don't have to put something else in the argon; just the argon itself is good enough for cleaning.
I think so. Yeah. Okay, that's it.
No, you see, and the SDC2, you have chlorine, or you have anhydrous HF in there, right? SDC2,
SDC2.
standard dry clean 2.
Uh-huh.
In that you have HF,
Yes.
right? Do you think it's going to clean silicon dioxide also? Like etch the whole silicon dioxide?
Yes, that's the purpose, one of the purpose, because silicon dioxide is formed in the first step, then it wants to be removed. So in order to remove particle in this,
Right, so it means there cannot be any pattern on the surface made of silicon dioxide. You cannot have any design in silicon dioxide on the surface.
design,
Pattern, photolithography pattern, silicon dioxide.
Yes, I think it's a process is used it's used before before some procedures like thermal procedures like oxidation, chemical vapor deposition. So there's supposed to be no pattern.
Right. So then how do you define which cleaning can be done in FEOL and which can be done in BEOL? You know, front end of line and back end of line. You know, they're different process for both. So how do you differentiate which one can be used BEOL and which can be used FEOL?
I think the whole process is it's before how to say it, BE or
So your cleaning is good only for BEOL, not FEOL.
like RCA.
Or just RCA, it's going to replace only RCA.
Yes.
Okay. Good question. Let's take the speaker. Who takes?
Hello everyone, I'm Farah Wandrewala and my topic for the term paper was self-aligned multiple patterning lithography. Now, pattern transfer involves two steps, lithography and etching. In lithography, it's the optical setup that is involved, wherein light is transmitted from the optical source, it passes through your mask and it develops a pattern on the resist. And in etching, the pattern is then transferred from the resist down to the functional layer. It could be whatever is your functional layer, silicon dioxide, or maybe directly onto the substrate. So until now, in pattern transfer, the minimum feature size that could be patterned on the wafer was the same as that was defined on the mask, which was used to transfer the light between the optical source and the wafer. In my method, so this is the relation between the resolution of lithography and depth of focus. As we know, resolution and depth of focus, there are trade-offs involved in matching both of them. Like if the wavelength is increased, then the resolution is improved, but the depth of focus is reduced. We don't want that. I mean, there has to be, there is an optimum numerical aperture that can be used with any given wavelength. So there are limitations in matching these two. These two are the trade-offs that need to be seen in any lithography system. So the need for multiple patterning arises is because the device sizes are shrinking day by day. The wavelength is not shrinking at the same pace. Reducing wavelength will reduce the feature size, but we can't, as of now, lithography is stalled at 193 nanometers. Any system performance is judged by how densely patterns can be replicated on the wafer. So even though the density is increasing, but the wavelength is not reducing at the same rate. That's why this method is proposed, wherein in this method the pattern lithography is used only as a pre-patterning process. Like the device dimension that is defined on the mask it could be 8 times more than that, which will ultimately result on the wafer. This is the relation that I propose. Like if APF, I will explain this equation will be more clear once I explain the process, but to give you an overview of the process, it's that the pattern is transferred from the mask onto the resist in one critical exposure. Critical exposure is your critical mask which has the device dimensions that are nearest to the ones that you want on the wafer. So, excuse me. Then etching is used to and there are multiple layers involved. So it's not like the mask will transfer the pattern. I mean, the resist does not cover the substrate directly. Depending on the feature size that you require on the wafer, there will be multiple layers through which the pattern will be transmitted and before it reaches the wafer. Etching is the key to this whole process. Deposition and etching. So, okay, that just dive right in, then this makes more sense. Now, sorry for the stretched out figure, but I could not get it to fit otherwise. This is my rough sketch of what a multiple pattern process would look like. This is the first step. This is your mask on which you have your critical dimensions defined. These are APF it's called advanced patterning film. It's a commercially available material that is used in this process. There are 3 layers. This is your silicon substrate on which you want your final pattern to go, but there are 3 layers before that. This is the first exposure where the photoresist is exposed. Now, then using oxygen plasma etching, APF is etched away. So this pattern of the photoresist is now transferred onto the first APF layer. This is called the first mandrel patterning. These are called mandrels. These are called mandrels and these are called spacers. Now what happens is once these are patterned, this is silicon nitride which gets deposited all over this. Due to constraints of space, I could not show all the steps, but this is how it works, that you deposit silicon nitride all over this, and then you etch away the silicon nitride using reactive ion etching, so that you get deposition only on either side of the mandrel. So this is a mandrel and these are the spacers. Then you etch away this APF layer, again using oxygen plasma etching, so that what you're left behind is with these spacers. Now this forms the first, now this is the first spacer template, which I will again etch APF to get this layer. So this is what was exactly below here. Sorry, I'm pressing the wrong button. This is what you get, which was exactly below here. So now if you can see, this defined only 2 lines, now there are 4. This is what's called double patterning. This is commonly used right now in fabricating memory devices like DRAMs. I am proposing to go extending this step. So then comes the third layer. This is again same way, again silicon nitride is deposited. So now again the number of lines keep doubling every time I do a mandrel spacer deposition and etching. So this is again when I etch away the second mandrel, this is what I get, the second spacer template. This is now 4 times of what was the original. This is the final mandrel, and these are the final spacers, which are now 8 times of what was originally defined. So, and these define the final lines which go onto the silicon substrate over here. Now one thing that happens is when you are doing this, this is the cross-sectional view, if you will, of, or the front view as you call it, of the lines. This is how they appear, but on the top they form loops at the ends of the wafer. So you need a second mask which will trim away those loops. You don't want those loops. You don't want those lines connected to each other. So this is the second mask which only exposes such that you can cut this part off. So it's, the rest of the whole thing is covered. You are only exposing this so that you can etch it away. This is called trimming of the closed loops. Then these are to add pads to the end. Now since these are lines, these are mainly used in memory devices, so these are bit lines and word lines. So you know you need to add your interconnects at the ends of these lines. So that's the second non-critical mask. Some papers have proposed combining this with the first step, so you can get rid of 2 masks, and so you can have only 2 masks to do your entire lithography, or you can have 3 masks. But there is only one critical mask no matter what method you use. Applications of this, like I said, it's high density of lines, so it's mainly used in DRAM fabrication as of now, and it is most suitable for uniform structures. As you can see, the spacer, this structure depends heavily on how these align with these. So it is highly preferred if the device is supposed to have uniform structures like arrays of lines together, so that they are they align themselves to each other. So that's what makes it, I mean, that's the asset of this method. But the drawback is that it can't be used for, I mean, it's still under research, but for non-uniform structures, like if I have a wider gate on one side and a smaller gate on the other, I may not be able to replicate that accurately. So the challenges that are faced with this is the choice of materials for the mandrels and spacers. Now that's critical, because what happens is it is observed that these can't go up to these can't have high aspect ratios, or else they collapse, they bend on each other, or they touch each other, which is not desired. So since etching is the key to all this, we need high selectivity in etching. So that so if I have to choose a mandrel, I have to choose something. Then the etchant should etch only the mandrel and not the spacer, or else I lose my whole purpose of doing this. So choice of materials is a very critical point in this process. Then there is the difference in critical dimension of spacer and mandrels. What this means is that spacers tend to have smaller critical dimension than the mandrel. Like these are more robust than the spacers are. The line width edge roughness, which is a figure of merit that is used, is higher in mandrels than it is in spacers. So that needs to be compensated for. Like, again, that comes back to the choice of material that is used, but then it also depends on the method of etching and the etchant that is used. And of course, increased processing steps. Now, depending on the density that I require, I'll have to keep doing multiple deposition, etching of the spacers. So that increases the cost of the whole system and the raw material, the etchants, and everything goes up, like the cost of chemicals and the processing steps. So there are methods that people are trying to come up with, like a mixture of chemicals that can perhaps do two types of etching within the same process. Like in this case, this oxide layer that you see, it is used for alignment between the mandrels. So there is a method which combines, when you etch away this, you etch away also the oxide, so you don't have to do two separate processes. All these etchings, especially for the mandrel and the spacer, takes place, it's reactive ion etching, because I need very anisotropic and very straight edges. Oxide layer etching is a wet etch process. Since it's a very thin layer oxide, a quick HF rinse is just done to get rid of it. As a conclusion, this method is the best so far. There are other methods like litho etch, where you do lithography etching on multiple layers. Then there is litho freeze, where you freeze the resist, you don't etch it away, but this is the one which gives the best device resolution. Again, the mask and device need not be the same. So the same wavelength, same lithography techniques that we use now, in fact the same mask that we use now, can be used for this process. And also this is extendable even to the next generation lithography like EUVL. When it comes into being, sooner or later we will reach the wavelength limit of EUVL also. So this can be used even to push it further until we come up with another solution. So coming back to the equation that I said, it's the multiple patterning level. Like if I need this to be 8 times of what the mask is, I will need 3 layers. So 2 to the power 3 will give me 8 times the pattern on the mask. If I need this to be 4, I just need 2 APF layers. That's how the equation works out. Now theoretically this works very well. Practically it remains to be seen how well it works. That's so. Thank you. Any questions? Yes, please.
So I think I missed something. Is this a way to surpass the resolution limit of the wavelength?
No, this is, yeah, you could say this is the way to circumvent the resolution limit of the wavelength. You don't change the wavelength, but you can still increase the device resolution.
Beyond the wavelength. Also, have you looked into, or looking into something similar? I saw this thing called interference lithography, where they create a standing wave pattern to limit repeating patterns. Do you know anything about that, or is this?
Well, I did read about it, but again, like I said, the key to this process is etching. So it was more deposition and etching are already defined steps. We already have the recipes for it.
This is basically state of the art right now. This is the
yeah, agreed. But then you would need that many lenses in between the source and the wafer. Whereas deposition, etching, already you can do it. It's well established. You don't need to change anything.
I see.
Whereas I know about your point where you put those multiple waveguides and do that, but then you would need to change your optical system for that.
So
my point is not to touch. the lithography system at all, just to use what's already available out there and improve if I can.
So I'm confusing. So this process is using more mask to improve some.
No, in fact, it uses only one mask. This is all etching and deposition. Once this is defined, this is the only mask that is used. Once this gets defined, then you just keep depositing and etching this part out. So this goes away. That's how you keep increasing your resolution.
How you can get the high aspect ratio, vertical?
It looks like a high aspect ratio, but it's. I mean, it could be high. I don't exactly know how high you can go in this, but this is using RI, reactive ion etching. You etch it away so that you get absolutely straight anisotropic structures.
Okay, so can we get enough vertical performance using this?
Yes, that's the whole point of it. Like, you keep depositing it on this, so you can keep scaling down, but again, there are limits to what you can go. It all depends on what material you use. Like I said, if this becomes too high, they may touch each other. So
at the first you told how we deal with depth of focus.
how we deal
This
with
technique.
it does not change the wavelength. So the depth of focus is for this. It remains the same. This part is your standard lithography that we do every day, optical lithography. But it's after this that the real thing starts.
Yeah, I have a question. Can you control the size of the green pearl?
Oh, this one? Yeah, this you can. It again depends on what this width is, because since it gets deposited on either side of it. Again, reactive ion etching is what will do that. So using that, you can control the width. It actually depends on what thickness I deposit over here. So if I deposit a thicker layer, then I can have a thicker.
From in the last two pictures, from the
This one?
slide, from the left diagram to right diagram, how do you come to this?
Oh, it goes this way. This is A, B, C, D. It's like this is the first step. Then
It's zigzag.
yeah, it's
I mean,
A, B, C, D, E, F.
I mean, if you want to pattern the silicon dioxide, I guess the green one is silicon dioxide layer.
This is silicon nitride.
Right, sorry, silicon nitride layer. If you want to pattern this, do you need another mask to do reactive ion etching?
No, you don't. That's the point.
When you go from step C to step D,
Yeah.
first you put a layer of silicon nitride on.
Yeah, when you put exactly. So you
How
have
do
to.
you etch away the region between the two spaces? With reactive ion etching.
With
you are
reactive
etching
ion
the
etching.
top part.
Yes, but again, like I said,
So you miss a couple of steps. You are to draw them. How would it look
okay.
like, and what you should? After you do deposition, what should the surface look like?
okay, if
How come there is selective etching in between those pillars? Which is not selective, but what happens?
this is your, this is the first mandrel. I deposit silicon nitride all of uniform thickness all over it. Now when I do reactive ion etching, I will etch away only this thickness. So this goes, this goes, this goes.
You are standing in front of them.
Sorry, this stays. I mean, you get that? So you'll end up with something like this. Like, it will etch only in this direction, not in this direction. So this will remain.
So this is what type of etch is this?
This is anisotropic.
Anisotropic.
Anisotropic dry etching. So, you see, only this region goes, while this still remains. That's how you get the spacers. Then when you etch this away, this will go away. This is oxygen plasma etch. Again, this is again a dry etching. So this will go away. So only the spacers remain. Now there is another APF layer. So this gets patterned exactly down. So again, I'll etch away all the other parts. So only these will remain. That's how it progresses.
Yeah, I see. So, which means you can control the size of the spacing.
Yes.
If you deposit less silicon nitride. So if you can do that, why do you need multiple layers? You just using one layers, but just deposit very.
Okay, I
little
understand your
time.
point. What you are trying to say is that if I have a very thin spacer, yeah, but you see, my problem is not this distance. My problem is this distance. I want to reduce this distance between the two. So if unless this does not get patterned down, and again it does not get this distance will not get reduced. You see? Getting the? Do you understand, or should I? Okay, I'll go one more here. These are the spacers that were created in the first. This is the second APF layer. This being thin is not a problem. This distance is what this is like, say, the channel length of the MOS device. So I need to reduce the channel length. So I need this to come down here so that I can again deposit silicon nitride, and then if you look at now, you can see this distance. That's the whole.
So you have if we understand correctly, you have the ability to selectively remove either the nitride or the oxide, so you keep alternating between nitride oxide, etc.
That is another method of doing it. But again, like I said, spacers are not very robust. Mandrels are what's more robust in maintaining the critical time. Like mandrels this will give me a very good edge, while the spacer will not. So if I do alternate silicon nitride and oxide, it will only be spacer deposition. That will not give a very good line critical dimension, or it will not be as accurate as it will be with
so
mandrels.
It doesn't scale differently. So given lambda, you said stagnated at 193 nanometers. What's the smallest feature you can make with this method right now?
Oh well, according to my equation, it could be anything. It just depends on the number of layers you use.
But what's the practical one they've achieved?
Practical, as of now, it's stalled at quadruple, so you can go up to 4 times that of what's on the mask.
Okay, so you basically can go to maybe 25 nanometers, 30 nanometers.
Yes.
Oh, cool.
So on the silicon substrate, you are using another layer, APF,
Yes.
right? So why you choose that material?
Oh, it's a standard patterning material that's used in the industry. I mean, you can use polysilicon, but polysilicon does not give very good edge roughness. This is a good one.
Can we use any material? Yes.
You can use any material you like, but again, like I said, choice of material is very important. There has to be edge selectivity between the spacer and the mandrel. So now, in case of nitride, what etches nitride does not etch the APF. So it is safe to use APF. Again, what etches APF, oxygen does not etch nitride. So when I etch one, I want the other to remain. That's the reason why I use this.
And the sidewalls are essential to this method, right?
Yes.
So what would be it's a trade-off, right? So we are increasing steps,
Yes.
right? We're increasing many more lithography steps, processing steps, which would increase failure also, which would increase the defects also, right?
It could, but like I said, this is for highly uniform structures. So if you're talking about memory devices, DRAMs, which only require lines in them and nothing else, it can be highly controlled. So it's highly likely that it
So
can
for
work.
highly periodic structures,
Yes.
this may be a better trade-off
Yes.
in terms of just because our structures are repetitive,
Yeah.
we will not have as much failure
Yeah.
as we might have with lines and circles and
Right, that's
rounds
right.
and rectangles.
Exactly. So the more uniform your wafer is going to be, the better it is now. All scaling as of now, it's measured in terms of how small a DRAM has got. So this is what's the extension.